Hello, and welcome to Beyond the Last Star. Wherever you are right now, whatever kind of day it has been, you made it here. And that is enough. Find a comfortable position. Let your body settle. If you can, turn the lights down low or off completely. Because tonight, we are not staying here. Tonight we are going somewhere most people never think to go. Past the last planet, past the edge of the sun's reach, into the deep and patient dark where the real universe begins. Before we leave though, drop a comment and tell me where in the world you are listening from right now and what time it is there. I read every single one. There is something I love about knowing that people from every corner of this small blue planet are drifting off to the same stars at the same moment. And if this is your first time here, welcome home. Hit subscribe so the next journey finds you. Now, are you ready? Let's go. Your day is over now. Whatever it carried, the weight of it, the noise of it, you can let it go. Because tonight we're going somewhere that no human being has ever truly been. And the journey there is long enough and quiet enough to carry you all the way to sleep. There is a star you have never heard of sitting in the darkness 124 light years from where you're lying right now. It is smaller than our sun, cooler, older in its habits. The kind of star that burns red and patient and slow, the kind that does not rush. Astronomers call it K2-18. It was discovered not because anyone was looking for it specifically, but because a space telescope called Kepler was watching hundreds of thousands of stars blink. And this one blinked at a particular rhythm, a particular dimming that meant something was crossing in front of it. Something round, something real, a world. And not just any world, a world that would, in the years that followed, quietly become one of the most discussed objects in all of human science. A world that made people ask, for the first time in a serious way, with data behind the question and instruments aimed at the answer, is there life out there? The planet is called K2-18b, and what makes it remarkable begins with water. Not the trace amounts found frozen into the poles of Mars, not the subsurface brines speculated about beneath the ice shells of moons, but an ocean, a real ocean, possibly covering the entire planet. This world, some models suggest, may be almost entirely ocean. No continents rising above the surface, no beaches, no cliffs, just water, stretching in every direction to every horizon under a rust-red sun that hangs permanently low in the sky, because K2-18b is much closer to its star than Earth is to ours. The year there lasts only 33 of our days. In the time it takes you to move through a single month on this planet, a full year has turned. K2-18b is larger than Earth, roughly 2.5 times larger by radius, and it belongs to a category of planet that does not exist in our solar system at all. We call them sub-Neptunes, or sometimes ocean worlds, or Hussein planets, a word made from hydrogen and ocean, because that is what they are thought to be. Worlds wrapped in thick hydrogen atmospheres, sitting above global oceans that stretch for hundreds of kilometers deep. We have nothing like it here. Jupiter is enormous, but mostly gas, no surface to stand on, no ocean beneath the clouds, just pressure that increases forever, until hydrogen becomes metal. Earth is small and rocky and wrapped in nitrogen. K2-18b fits in the space between those things. It is something else entirely. A category of world we are only beginning to understand, and this one, in particular, has offered us something extraordinary. In 2023, the James Webb Space Telescope, the largest, most powerful space telescope ever built by human hands, a mirror the size of a tennis court folded like origami into a rocket, and sent 1 million miles from Earth, turned its instruments toward K2-18b as the planet crossed in front of its star. The starlight passed through the edges of the planet's atmosphere. Certain wavelengths of light were absorbed by the gases there, others passed through, and the telescope recorded exactly which ones. That pattern of absorption is a fingerprint, a chemical signature, and what it revealed, buried inside that atmosphere 124 light-years away, was a molecule called dimethyl sulfide. The letters, if you want them, are DMs. On Earth, and this is the part that matters, dimethyl sulfide is produced by living things. specifically by marine phytoplankton, tiny ocean organisms, life, biological life, metabolizing, existing, releasing this molecule as a byproduct of being alive. On Earth, DMS is a biosignature, something only life makes, and there it was, faint but detectable, in the atmosphere of an ocean world orbiting another star. No one said the word proof. Scientists are careful with that word, and rightly so. The signal was real, the data was real, but the quantity was uncertain. The sources were multiple possibilities, and the universe occasionally produces chemical mimics, molecules that look like life from a distance but have geological or photochemical origins. Researchers noted it. They published it. They were cautious and honest about what it might and might not mean. And yet, even as they wrote carefully about uncertainty, something had shifted. Because dimethyl sulfide had never been detected in an exoplanet atmosphere before. Not once. This was the first time. And it was found not on a random rock drifting through space, but on an ocean world. A world with liquid water, a world sitting inside the habitable zone of its star where temperatures could allow that water to stay liquid. A world, in other words, that had every quality we have been trained to associate with life. The question is not a small one. It is perhaps the largest question human beings have ever asked in any serious scientific sense. Are we alone? Not philosophically, not religiously, but actually physically, cosmically. Are there other living things in the universe? And K2-18b, in this quiet, careful, provisional way, had begun to answer. To understand what life on K2-18b might actually look like, if it is there at all, you have to first understand what the planet's surface is actually like. The word ocean is familiar, but this ocean is not the Atlantic. It is not blue in the way you picture it. The star K2-18 burns at about 3,500 degrees Kelvin compared to our Sun's 5,500. Far cooler, which means it glows orange-red rather than yellow-white. If you were somehow floating above the ocean of K2-18b, the sky above you would be dim and deeply coloured. Not black, not blue, but something ruddy and dense, a sky full of hydrogen and methane, the light filtering down the way light filters through amber glass. The ocean below you would look strange. The colour of it would depend on what lived in it, if anything lived in it, but against that reddened sky the water would absorb and scatter the light differently than Earth's oceans do. It might look darker, more like ink, more like the deep ocean trenches here on Earth, where sunlight never reaches and life exists in the pressure and the cold and the chemical seeps of the seafloor. That comparison to Earth's deep ocean is not accidental. When scientists imagine what life might look like in a Haitian ocean, they often look down rather than out. They look not to the stars, but to the deepest trenches of our own seas, where creatures live without sunlight at all, sustained by the energy of hydrothermal vents, chemical reactions, heat from the planet's interior. This kind of life is called chemosynthetic. It does not need photosynthesis. It does not need the star, it only needs chemistry. And chemistry, in an ocean as vast as K2-18b's, would exist in abundance. Minerals, dissolved gases, temperature gradients where cold water meets warm rising currents from below. If life there exists at all, some researchers believe it may be entirely independent of the red star above it, living in the deep places of a world ocean, producing as a side effect the very molecule that drifted up through kilometers of water and kilometers of atmosphere and travelled 124 light-years to a telescope mirror in space and arrived as a whisper in a dataset. Imagine that for a moment. A microorganism, something smaller than a grain of sand, something with no eyes, no language, no concept of starlight or distance, living in the dark pressure of an alien ocean, metabolizing sulfur compounds, dividing and reproducing and drifting in the slow currents of a world it cannot comprehend. And through the simple chemistry of its existence, it exhales dimethyl sulfide. That molecule rises, diffuses through the water, reaches the surface, enters the atmosphere, climbs through layers of hydrogen and methane, exits the atmosphere, travels for 100 to 24 years at the speed of light, enters a mirror, becomes data, becomes a question, becomes the most important question a species has ever asked itself. Are we alone? The phytoplankton of Earth's oceans produce about 1 billion kilograms of dimethyl sulfide every year. It is one of the primary ways the ocean communicates with the atmosphere, how marine life influences cloud formation and climate. This is not a rare or delicate process. It is vast and constant and has been happening for hundreds of millions of years. When researchers attempted to calculate how much DMS would be needed in K2-18b's atmosphere to produce the signal Webb detected, the numbers were unsettling. Orders of magnitude more than Earth's oceans produce, which either means the signal was uncertain and may not represent what it seemed to, which is the cautious and responsible interpretation, or it means that if DMS is truly there, the ocean producing it is something unlike anything on Earth. A biosphere, perhaps, of incomprehensible scale. An ocean alive not at the edges, not in patches, but everywhere, all at once, billions of square kilometres of it teeming. The James Webb Space Telescope was not designed specifically to search for life. It was designed to see further, deeper, older, to look at the first galaxies that formed after the Big Bang, to study how stars are born inside nebulae, to map the chemical compositions of worlds. But in looking at everything, it found this. In the process of being a scientific instrument aimed at all of the universe, it found a signal in an ocean world sky that made the people who built it go quiet. That quality of scientific quiet, not silence, but a held breath, a suspension of normal speech, is itself remarkable. These are people who think about the universe every day, who are accustomed to large numbers and ancient timescales, and the routine strangeness of deep space. And still this made them pause. Part of what makes K2-18b so compelling, beyond the DMS signal, is how well it fits the theoretical profile of a place that could harbour life. The habitable zone, the range of orbital distances from a star where liquid water can exist on a planet's surface, is sometimes called the Goldilocks zone, the zone that is not too hot and not too cold. K2-18b sits comfortably inside this zone. Its star is smaller and cooler than ours, so the habitable zone is correspondingly closer in, and K2-18b's tighter orbit still keeps it at the right temperature. Liquid water is not just a nice feature for life. As far as we know, it is the foundation. Every living thing we have ever found, without exception, requires liquid water. It is the solvent in which chemistry becomes biology. And K2-18b appears to have it in extraordinary quantities. The atmosphere above that ocean is also relevant. Thick hydrogen atmospheres, researchers have argued, may actually act as insulation, keeping the surface of a Hycean world warmer than it would otherwise be, extending the habitable conditions deeper into the planet's history, giving life longer to begin. The very hydrogen that makes the atmosphere alien and unlike our own may be the blanket that allowed the ocean below to stay warm enough, long enough, for something small and chemical and persistent to take hold. Life on Earth did not appear immediately after the planet formed. It took hundreds of millions of years. Life needs time as much as it needs water. K2-18b has had time. Its star is old. The system is old. If life was going to happen there, it has had every opportunity. There is a strange intimacy in that thought if you let yourself feel it. The universe does not care about intimacy. It does not care about any of this. The distances involved are beyond comprehension. 124 light-years means that the light leaving K2-18b right now, at this moment, will not reach Earth until the year 2148. The civilization, if there is one, will never know we exist. The microorganism, if it exists, does not know it has been detected. And yet here you are, in the dark, in your bed, at the edge of sleep, thinking about another ocean on another world. And something in that stretch of attention feels like the best thing a mind can do. Reach across impossible distance. Find something real. Care about it. Astronomers plan to keep looking. The DMS detection was preliminary, a first pass, a tantalizing result that requires confirmation before anyone will let themselves truly believe it. Webb will observe K2-18b again, and again after that, building up more data, refining the signal, ruling out non-biological explanations one by one. This is how science works, not in a single dramatic revelation, but in accumulation, in patient returning, in the slow building of confidence. Each observation adds a layer. Each layer makes the picture clearer, and somewhere in the next decade, perhaps sooner, the picture may become clear enough to say something that has never been said before in human history. But for now, in the absence of certainty, there is something even more beautiful. The possibility itself. The open question. The not yet knowing. Because in the space between question and answer, the imagination is free to travel, and tonight your imagination can travel all the way to an ocean world with an amber sky and a deep, quiet sea, where something too small to see is making a molecule that crossed the universe to be found. The telescope that found it is sitting right now at the L2 Lagrange point, a gravitational balance point in space, about 1.5 million kilometers from Earth, always staying on the side of Earth away from the sun so that Earth's shadow keeps its mirrors cold. It is cold out there, nearly 233 degrees below 0 Celsius. The telescope needs to be that cold because it observes infrared light, heat radiation, and if the telescope itself were warm, its own heat would drown out the faint signals from distant worlds. The cold is what gives it sight. The cold is what let it see K2-18b's secret. And it floats there, turning slowly, pointed this week at something ancient, pointed next week at something new, doing its quiet work in the dark. The story of how we got here, how a species that lived entirely on one small wet rock came to be pointing mirrors at other worlds and reading the chemistry of their skies, is itself extraordinary. It begins with curiosity, which is the oldest and most reliable engine of human progress. Curiosity about what the lights in the sky were. Curiosity that drove the first astronomers to map them, to notice patterns, to predict eclipses and solstices. That curiosity grew instruments, lenses, mirrors, radio dishes, photon detectors. It grew mathematics capable of describing the motion of things across billions of light years. It grew rockets capable of leaving the atmosphere and placing the most sensitive instruments ever built into the frozen silence of space. All of it, every step of thousands of years of looking up was pointed toward this, the moment when we could ask the question seriously. Are we alone? And begin to hear the answer form. K2-18b did not ask to be found. It did not broadcast a signal. It simply crossed in front of its star and we noticed. It simply had an atmosphere and we read it. The universe does not announce itself. It waits to be discovered by whoever is patient enough and curious enough and quiet enough to look. There are other ocean worlds in the universe, almost certainly. The models that describe Hessian planets suggest they should be common, perhaps the most common type of potentially habitable world in the galaxy. If K2-18b is alive, it may not be unusual. It may be one of millions, billions even. A universe not of rare, isolated exceptions, but of oceans, everywhere, in the dark between the stars, each one its own chemistry, its own currents, its own quiet processes that may or may not have, somewhere in their long histories, crossed the threshold from chemistry into life. The threshold is the mystery. We know life began on Earth. We are the proof. We know it began in water, in warm shallow pools or deep ocean vents, in a primordial chemistry that somehow, in a process we still do not fully understand, became self-replicating. The first living molecule. The first thing that could make a copy of itself. Everything that has ever lived on this planet, every organism that has breathed or grown or reproduced, every redwood and blue whale and bacterium is descended from that first threshold crossing. One event, billions of years ago, and the entire tree of Earth life grows from it. The question K2-18b poses is whether that threshold can be crossed twice, whether it has been crossed elsewhere, whether it is, in fact, crossing right now, in some warm pressure zone of a hydrogen-wrapped ocean, in the dim reddish light of a smaller star, where the chemistry is different, but the principle is the same. Some scientists believe life is inevitable wherever the conditions are right, that it is not an accident but an attractor, a state that chemistry tends toward under the right circumstances, the way water tends downhill, the way heat tends to spread. If they are right, the universe is full of life. If they are wrong, and life is an accident so improbable that it has happened only once in all of cosmic history, then we are something stranger and more miraculous than we can quite bear to think about. Either answer is astonishing. Either answer makes the question worth asking. And K2-18b, with its amber sky and its deep hidden ocean, and its whisper of dimethyl sulfide, is the clearest place we have ever aimed that question and heard something that might, just might, be an answer forming in the dark. The ocean of K2-18b, if it is there the way models suggest, is unlike anything in human experience. It may be hundreds of kilometers deep. Earth's oceans average about 3.7 kilometers. The deepest point, the Mariana Trench, descends about 11 kilometers. K2-18b's ocean may be 100 times that, 200 times. The pressure at the bottom of such an ocean would be almost unimaginable, far beyond the crushing depths of our own deep sea. At extreme pressures, water itself changes phase. It does not freeze in the normal way. It becomes a form of ice called high-pressure ice, different from the ice in your freezer, ice that exists not because of cold, but because of pressure. This exotic state of matter, sometimes called Ice 7, is hard and strange, and it may form the floor of K2-18b's ocean, a solid base not of rock but of pressurized water in a crystalline state. Life as we know it would struggle in those conditions, but life as we know it is not the only kind possible. And in the middle layers of that ocean, far from the crushing floor, far below the stormy interface with the hydrogen sky, there may be zones of moderate pressure and moderate temperature, where the chemistry is permissive, where molecules can form and dissolve and interact and, over billions of patient years, perhaps become something. The star K2-18 has been burning for approximately 2 to 3 billion years. Earth took about 600 million years to develop its first microbial life after formation. K2-18b has had time, possibly much more time than Earth needed. The ocean has been there, sitting in the dark and the pressure and the diffuse reddish warmth, long enough for something to begin. You're listening to a story about a world that may be alive, told by a species that only recently learned to look, and the looking is still happening. Right now, tonight, while you are here in the quiet and the dark, the James Webb Space Telescope is doing exactly what it was made to do. It is collecting photons, ancient light that has crossed the galaxy and entered its mirrors and become numbers that humans will interpret in the morning. It never sleeps, it never stops. In the cold and the silence of L2, it simply keeps looking, patient as the universe itself. There is something about that patience that the mind can hold on to. The universe is not in a hurry. The stars burn for billions of years. The oceans of alien worlds move in currents measured in geological time, slow as continents, steady as deep cold. Even the DMS molecule, if it is truly there, truly rising from a living ocean, rises slowly through kilometers of water and kilometers of air, drifting upward, not in moments, but in months, in years, a molecule taking the long way toward the light. Everything at this scale is slow. Everything at this scale is patient. And there is something in that slowness that the body recognizes, something that the mind, given permission, can begin to match. The tempo of the universe is not hurried. It never has been. The star K2-18 will burn for another 50 billion years. Our own sun has about 5 billion years remaining. K2-18 will outlast ours by an extraordinary margin. Small, cool stars burn frugally, conserving their fuel, lasting longer than the bright and brilliant ones. When our sun has expanded and dimmed, and the inner solar system has been remade by its death, K2-18 will still be burning. If life is there now in that ocean, it has time beyond comprehension ahead of it. Time to evolve, time to grow complex, time to perhaps look up through whatever equivalent of eyes it might someday develop, through kilometers of ocean and layers of hydrogen sky, and wonder what the lights are. That thought, the thought of life on K2-18b eventually developing the curiosity to ask its own questions, is not science. It is imagination, which is its own kind of instrument. But the imagination does not need to apologize for traveling there. The science brought us to the edge of that ocean. The imagination can see the currents in it. And tonight the two are not so different. Both are forms of reaching. Both are forms of not being satisfied with the small and the close and the already known. There is a particular kind of quietness that comes when you have followed a thought all the way to its furthest point. When you have crossed the distance between your bed and an ocean world orbiting a red star 124 light-years away, and arrived there and looked around at the amber sky and the ink-dark water and the incomprehensible depths, and let the strangeness of it sit with you. That quietness is not emptiness. It is fullness held still. It is what happens when the mind has gone somewhere genuinely far and returned changed, even slightly, even just by having considered the scale of things. The ocean of K2-18b turns slowly in its planetary currents, shaped by a gravity slightly stronger than Earth's, under a sky that does not look like any sky you have ever seen. The star above it is a deep orange ember, close enough to be larger in the sky than our sun appears to us, but dimmer, redder, less white and burning. The light it casts on the ocean's surface, if there is a surface, if the ocean ends somewhere before the sky, is the colour of an old fire seen through water. Warm in hue but not in feeling. The kind of light that suggests depth rather than illuminating it. And somewhere beneath that surface, in the middle pressure zones where the chemistry has had billions of years to work, something may be happening that has no name in any human language yet. Not intelligence, not complexity. Just the first and most fundamental property of life, self-replication. One molecule making another molecule in its own image. The universe folding back on itself, becoming aware of itself in the smallest and most ancient way. The signal that left K2-18b and arrived in the James Webb Space Telescope was made of starlight. The star's light passed through the atmosphere, and the atmosphere left its mark on that light, and the telescope read the mark. What we detected was, in a sense, the star speaking through the planet's air. The star's photons, altered by the presence of a particular molecule, arriving at our mirror with a message written in absorption lines, chemistry as language, distance as delay. 124 years between the sending and the reading, whatever made that signal, whether biology or geology or some process we have not yet imagined, it has been making it for longer than human civilization has existed. The DMS in K2-18b's atmosphere, if it is there, has been rising for perhaps millions of years. The ocean that produced it, if an ocean produced it, has been turning for longer still. This is not a new event we detected. It is an ancient, ongoing process that has been happening without our knowledge for the entire span of human history and further back. We simply learned to look in time to catch it. And just below the deepest layers of that ocean, at the boundary where water becomes ice under pressure, where the temperature is coldest and the dark is most complete, something in the chemistry has been turning over and over for longer than we can say. Patient as stone, quiet as distance, waiting without knowing it is waiting, the way all things wait before they are found. The universe does not explain itself. It simply continues, one process leading into another, one discovery opening into a deeper question. The way a door opened in a dark hallway reveals not a room but another hallway, longer, quieter, and more interesting than the first. We left K2-18b at its deepest place, at the pressure boundary where water becomes something harder and stranger than water, where the cold and the weight of an entire world ocean pressed down on a floor made not of rock, but of crystalline ice, under forces that have no equivalent in ordinary experience. But the story of this world does not live at the bottom. It lives in the middle, in the layers between the crushing floor and the turbulent sky, in the zone where pressure is survivable and temperature is moderate and chemistry is free to move. That is where life, if it is there, has made its home. And to understand what that home looks like, it helps to understand what we mean when we say ocean. On Earth, the ocean is a single connected body of water divided by continents and currents into named regions: the Pacific, the Atlantic, the Indian, the Arctic, the Southern. But beneath the names it is one thing, one system, circulating, mixing, driven by the rotation of the Earth and the heating of the Sun and the pull of the Moon. The ocean has memory. It stores heat from the tropics and carries it toward the poles. It absorbs carbon dioxide and releases oxygen. It moderates the climate the way a thermal mass moderates the temperature of a room. The ocean is not a backdrop to life on Earth. It is in many ways a living system itself, the medium through which the chemistry of the biosphere flows. K2-18b's ocean, if the models are correct, would be a single unbroken body of water covering the entire planet. No continents to divide it, no beaches at the edges, just ocean in every direction, meeting the sky at a horizon that curves away more steeply than Earth's because the planet is larger. The currents in such an ocean would be driven by the same basic forces: rotation, temperature differences, the gravitational influence of the star, but without land masses to deflect or channel them. They would move in great unbroken gyres, enormous slow circles that take years or centuries to complete. The mixing would be different. The chemistry would distribute differently, and life, if it were there, would not be concentrated in shallow coastal zones the way so much of Earth's marine life is. It would be distributed across the whole surface and the whole depth of a world entirely covered in sea. The upper layer of K2-18b's ocean would be most exposed to the energy of its star. Not sunlight as we know it. K2-18's radiation peaks in the infrared and near-infrared rather than the visible spectrum, but energy nonetheless, filtering down through the hydrogen atmosphere and striking the ocean surface in wavelengths that a photosynthesizing organism might use if evolution had led to something like photosynthesis there. Earth's plants and algae evolved to use the specific wavelengths our Sun provides most abundantly. Life in K2-18b's ocean, if it photosynthesizes at all, would use different wavelengths. It might appear to human eyes a completely unexpected colour. Not green, perhaps deep red or near black, optimized to absorb the infrared radiation of a cool red star the way Earth's plants are green because they reflect the yellow-green wavelengths our Sun provides in excess. A world ocean full of near-black photosynthetic life. Trillions of organisms tinting the surface of the water a colour that has no human name, stretching from horizon to horizon under an amber sky, absorbing the dim red light and turning it into energy, and releasing, as a byproduct of their chemistry, dimethyl sulfide into the air above them. That is one picture, one possibility among many. But it is grounded in real biology, in the known principle that life evolves to use what is available, that it fills whatever energetic niche exists with remarkable consistency and creativity. Of course, there is another picture, and it does not require sunlight at all. The hydrothermal vents of Earth's deep ocean were discovered in 1977, and they changed everything we thought we knew about where life could exist. Before that discovery, the assumption was that all life on Earth ultimately depended on the sun. The food chain began with photosynthesis, and everything else ate something that had photosynthesized. The vent discovery shattered that model. At the bottom of the Pacific, in total darkness, under pressures that would destroy any unprotected human, communities of organisms were living in complete independence from solar energy. Tube worms meters long, white crabs, strange shrimp, fish adapted to absolute darkness, all of them sustained by chemosynthetic bacteria that drew their energy not from the sun but from the chemical reactions occurring where superheated mineral-rich water met cold ocean. Hydrogen sulfide, methane, iron, these were the fuels. Life had found another way in entirely. If K2-18b has a geologically active interior, and there is no reason to think it does not given its size and the timescales involved, then its deep ocean floor would be dotted with hydrothermal vents, places where the heat of the planet's interior escapes through cracks in that pressurized ice floor, where mineral-rich superheated water jets up into the cold and the dark and the waiting chemistry. These would be, potentially, the most hospitable places on the entire planet for life as we understand it. Away from the radiation of the surface, away from the violence of the atmosphere-ocean boundary, in the steady, reliable, ancient warmth of geothermal energy, surrounded by the chemical complexity that vent systems produce. Life at the floor of K2-18b's ocean would not need the star at all. It would be entirely self-contained, drawing on the planet's own interior heat, the way a fire draws on the wood beneath it. And the DMS that the James Webb Space Telescope detected, the molecule that started all of this wondering, could be rising from those depths. Produced by chemosynthetic organisms living in the vent communities of a high-pressure ice floor, 200 kilometers below the ocean surface, diffusing upward through centuries of slow current into the upper ocean, crossing the surface, entering the thick hydrogen atmosphere, rising through kilometers of gas to the edge of space and escaping into the void, where, 124 years later, it arrives at a mirror. That chain of events, if it is what happened, is among the most extraordinary things the universe has ever done, entirely unintentionally. A microorganism producing a molecule as a metabolic byproduct, with no knowledge that it is doing so, and no awareness that the molecule will travel to another star system and change the way a distant species thinks about itself. Biology generating meaning across distances it cannot conceive. The universe, in its patient and indifferent way, making something that looks very much like a message out of nothing more than chemistry and time. The team at the University of Cambridge that led the analysis of the Webb data spent months examining alternative explanations. Could the DMS signal be produced by photochemistry, by the action of ultraviolet radiation on other atmospheric molecules, creating DMS without biology? The calculations were done, the photochemical production rates were estimated. The conclusion was that photochemistry alone could not plausibly account for the concentration suggested by the signal. Could it be a geological process? Volcanic outgassing, perhaps? Or some mineral reaction at the ocean floor? This was examined too. And while geological sources of sulfur compounds exist, the specific signature of dimethyl sulfide in those quantities did not match any known abiotic process convincingly. The biological explanation remained the simplest, not proven, but the simplest, and in science, simplest is a meaningful word. It is not the same as correct, but it is where the careful money goes while more data is gathered. More data is being gathered now. The James Webb Space Telescope has been scheduled for additional transits of K2-18b, additional opportunities to watch the planet cross its star and read the atmosphere again. Each transit gives more photons, more signal, more statistical confidence. The uncertainties will shrink, the picture will clarify. And at some point, probably within this decade, the signal will either grow stronger with accumulating evidence, or it will weaken, revealing itself to have been noise or a misidentification, and the question will remain open and science will look elsewhere. Both outcomes are valid, both outcomes are how knowledge grows, but the watching continues regardless. Other molecules are being searched for simultaneously. Dimethyl sulfide is one biosignature, but life produces many chemicals. Oxygen, methane in certain combinations, nitrous oxide, phosphine, possibly under the right conditions. A world with a genuine biosphere would not produce only one chemical signal, it would produce a suite of them, a fingerprint not of one molecule but of a system, a metabolism, an ecology. The more signatures align, the stronger the case. K2-18b's atmosphere currently shows methane and carbon dioxide in proportions that are consistent with a Hycean world, and the DMS on top of that is the piece that does not quite fit a purely geological explanation. Future observations may add to that picture, or subtract from it. The universe withholds its secrets carefully and releases them one photon at a time. There is a researcher at MIT named Sarah Seeger, who has spent her career thinking about exactly this problem: how to detect life on worlds we cannot visit, how to read a biosignature from a light year away, how to design instruments sensitive enough to find biology in the chemistry of alien skies. She developed a concept she calls the planetary fingerprint, the idea that a living world produces a specific combination of atmospheric chemicals that a dead world cannot, and that if you can read those chemicals accurately enough, you can distinguish the living from the non-living across any distance. K2-18b is, in a way, the first real test of that concept. The first time the instruments have been good enough to even attempt the reading. And what they found when they tried, for the first time, was something that should not be there if the world is dead. Seeger herself has spoken about the discovery with the particular combination of excitement and discipline that characterizes the best scientists. People who desperately want the thing to be true, and who work hardest to prove themselves wrong before they allow themselves to believe it. She has said, in various forms, that this is what they built the tools for, that this is the question the field exists to answer, and that the answer is not yet clear, but the question has never been asked this well before. You are travelling tonight through one of the genuine frontiers of human knowledge, not a place of settled facts and confident conclusions, but a place where the instruments are good and the data is real, and the question is open, and the answer is forming slowly, the way starlight forms, not all at once but photon by photon over time, until there is enough of it to see by. The ocean of K2-18b covers a surface area roughly 6 times larger than Earth's total surface. 6 times. Every ocean, every sea, every lake and river and polar ice sheet on our entire planet. Take all of that water and spread it over 6 times the area, and then keep going downward for hundreds of kilometers instead of a few. The sheer volume of that ocean is a number that the mind accepts but cannot actually hold. It is the kind of quantity that has to be approached sideways through comparison. The Pacific Ocean contains about 710 million cubic kilometers of water. K2-18b's ocean may contain hundreds of times that, thousands of times. A body of water so immense that the whole history of Earth's marine biology would be a small and local experiment by comparison. And yet, even in that vastness, life, if it is there, would follow the same principles it follows here. It would cluster near energy sources, it would evolve to fill niches, It would compete and cooperate and diversify and go extinct in some lineages and flourish in others. The scale would be incomprehensible, but the logic would be familiar, because the logic of life is chemistry, and chemistry follows rules that do not change from one ocean to another, from one planet to the next. Carbon forms long chains. Phosphorus carries energy in molecular bonds. Water dissolves things. Gradients of temperature and chemistry drive processes. These are not Earth-specific principles. They are universal ones. Somewhere in the upper currents of that vast dark ocean, near enough to the surface that the dim infrared light of K2-18 reaches it in some usable form, there may be organisms drifting, passive, tiny, shaped by billions of years of selection into forms that are efficient and strange by any standard we could apply. They would not look like the phytoplankton of Earth's oceans. They would not be green. They would not have cell walls made of the same materials, but they would have some equivalent of a membrane, some way of separating inside from outside, some chemistry that concentrates what is useful and expels what is not. Because that is what being alive means, at the most basic level. Maintaining a difference between yourself and the environment, using energy to hold that difference in place, reproducing before the energy runs out. A simple definition, a universal one perhaps. The light above them would be red and filtered. The pressure around them would be greater than anything on Earth's ocean surface. The chemicals dissolved in the water would be different. More sulfur compounds, more methane-derived materials, a chemistry shaped by a hydrogen atmosphere rather than a nitrogen-oxygen one. And still, perhaps, they drift, dividing, metabolizing, releasing their small chemical signatures into a water column that carries them upward and outward, the way Earth's ocean carries things, slowly, steadily, following gradients and currents and the patient pull of a world's gravity and spin. The word alien is almost too simple for what K2-18b's life, if it exists, would actually be. Alien suggests difference, foreignness, the other. But life on K2-18b, if it is there, would not be other in the way we usually mean it. It would be related to us in the most fundamental sense, not biologically, not genetically, but logically. It would be another instance of the universe doing the thing the universe apparently does under the right conditions, given enough time, organizing chemistry into something that persists, that replicates, that changes over time. If K2-18b is alive, it is not other. It is kin. A different solution to the same problem, a different story written in the same language. That is perhaps the most humbling and the most consoling thing about this search. It is not a search for something foreign and threatening. It is a search for family, for proof that the conditions that produced us are not unique, that the chemistry that makes life possible is not a local accident, but a universal tendency, that somewhere in the dark and the distance and the extraordinary variety of worlds the cosmos has made, something else has found the same threshold we crossed and stepped across it, in its own way, in its own ocean, under its own dim star. The James Webb Space Telescope will continue its work. The data from K2-18b will be analysed and reanalyzed. Theoretical models will be refined. New instruments, the next generation of space telescopes, larger and more sensitive still, currently being designed and debated and funded in pieces, will eventually turn their mirrors toward this system and read it at wavelengths we cannot currently access. The story is not finished. It has barely begun. And in the meantime, the ocean of K2-18b turns in its slow gyres under its amber sky, indifferent to being watched, indifferent to the question we are asking about it, carrying in its currents and its chemistry the answer to the oldest question a conscious mind has ever asked. Patient, dark, vast, and perhaps in the deep places where the vents breathe their minerals into the cold, alive in a way that has been alive for longer than we have existed to wonder about it. The signal travels, the light crosses the distance, the telescope collects it, and somewhere in the data, folded into the absorption lines of a molecule too small to see, the universe is beginning, very slowly, very carefully to answer. There are other molecules in K2-18b's atmosphere that have not yet received the attention they deserve. Carbon dioxide is there, which is expected. It is a common atmospheric gas and appears on many worlds without any implication of biology. But the ratio of carbon dioxide to methane is unusual. On a purely geological world, exposed to ultraviolet radiation and the chemistry of a hydrogen atmosphere, methane tends to be destroyed faster than it is produced. Its presence in detectable quantities suggests it is being replenished. And the thing that replenishes methane most efficiently on Earth is biology. Microorganisms called methanogens, ancient lineages of single-celled life that metabolize hydrogen and carbon dioxide and release methane as a byproduct, have been doing this since before the oxygen in our atmosphere existed. They live in swamps, in the guts of animals, in the sediments of the deep ocean floor. They are among the oldest living things we know, and they are precisely the kind of organism you might expect to find in the deep, hydrogen-rich ocean of a Haitian world, where their primary ingredients, hydrogen and carbon dioxide, are available in extraordinary abundance. If methanogens, or something chemically analogous to methanogens, are living in K2-18b's ocean, they would be producing methane continuously. Releasing it into the water, the methane would rise, as gases do, through the water column and into the atmosphere above, and there it would be, sitting in the spectrum of a planet's air, waiting to be read by a telescope cold enough and precise enough to find it. The methane signal in K2-18b's atmosphere may not be proof of life, but it is consistent with life. It fits the picture. It adds to the fingerprint. And every piece of the fingerprint that fits makes the picture harder to explain without biology. This is how the case is built, not with a single piece of irrefutable evidence. That almost never happens in science, and certainly not in astronomy, where you can never go and check directly. But with a convergence of consistent signals, each one explainable in isolation by non-biological means, but together forming a pattern that becomes increasingly difficult to attribute to coincidence. A world in the habitable zone, a global ocean, a hydrogen atmosphere suggesting the ocean is real and deep, carbon dioxide and methane in suspicious ratios, and dimethyl sulfide, the molecule that, on Earth, has only ever been made by life. One by one the pieces land. The star K2-18 is so much quieter than our own sun. Our sun erupts regularly, solar flares, coronal mass ejections, bursts of radiation that can disrupt satellites and paint the poles with auroras. K2-18 is cooler and less violent in its higher energy output, though red dwarf stars have their own kind of activity, particularly when young, sending out strong flares of ultraviolet and X-ray radiation that can strip away planetary atmospheres if the planet has no magnetic field to protect it. Whether K2-18b has a significant magnetic field is not yet known. If it does, the ocean below would be shielded from the worst of the stellar radiation, allowing chemistry to proceed without being constantly disrupted. If it does not, the upper atmosphere may be more hostile than the models suggest, and life, if it exists there, would be confined to deeper layers where the radiation does not penetrate. Depth, in this ocean, is not just a physical quality, it is a kind of protection. The deeper you go, the more the water above you shields you from the sky. In the middle and lower layers of a Haitian ocean, the radiation from even an active red dwarf would be attenuated to nearly nothing. Life there would be living in a radiation environment far more stable and gentle than the surface of any rocky planet with a thin atmosphere. The ocean itself is the protection. The vastness of it is what makes the deep places safe, and safe places, given time, are where life tends to go. You have been travelling a long way tonight, through the telescope and the data and the careful language of detection, through the pressure zones and the vent systems and the slow chemical logic of a world entirely covered in sea. The distance between here and there is one of the largest numbers the human mind is asked to hold. 124 light years, 1.17 quadrillion kilometres, a span of space so enormous that even light, the fastest thing in the universe, takes longer than a human lifetime to cross it. And yet here you are, having crossed it in imagination, standing at the edge of an alien ocean and looking down into the dark water, wondering what moves in it. The wondering is the point. The wondering is what makes us different from the rocks and the gas and the empty space that makes up most of the universe. The universe is mostly not wondering about anything. It is mostly just happening, expanding, cooling, burning, colliding, decaying. And then in a small percentage of the matter, in warm oceans on certain worlds that orbit at the right distance from the right kind of star, something begins that eventually looks up and asks. K2-18b may have that something in it. We may not be as alone in the asking as we thought. The night is quiet where you are. The distance between your ceiling and the stars above it is incomprehensible, but it is the same distance that connects you to K2-18b, the same unbroken fabric of space that the telescope's data travelled through on its way to a mirror, and then to a computer, and then to the minds of researchers who went quiet for a moment before they began to write. That quietness, that pause before the careful language of science resumed, is something you can share even now, even from here, even at this distance. Something was found. Something that might be life. Something that might mean the universe is not empty in the way the empty dark between the stars suggests. And deeper in that ocean, in the layers where the cold settles and the currents slow and the chemistry works its patient work without hurry or interruption, something may be exhaling a molecule that will cross the universe again tonight, the way it has been crossing for longer than we know, carrying in its structure the simplest and oldest message that life can send. Not language, not intention, just the chemical proof of existing, on its long way toward a mirror we have not yet built. There is a moment in every long journey when the destination stops feeling distant and starts feeling real, when the maps and the measurements give way to something more immediate, more felt. You have been travelling toward K2-18b for 2 nights now, through the data and the telescopes and the careful language of science, and tonight the journey changes. Tonight the ocean becomes something you can almost touch. Let the science become poetry for a while. It has earned that. The ocean of K2-18b is old in a way that has no good comparison in human experience. Not old like a grandparent, not old like a mountain, not even old like a fossil pressed into limestone over millions of years. Old like a star, old like the time before Earth existed. The water molecules that make up that ocean were forged in the early universe, hydrogen atoms produced in the first minutes after the Big Bang, oxygen atoms manufactured inside stars that lived and died before our sun was born. The ocean of K2-18b is, in a very real sense, made of the oldest material in the universe, assembled into water by the chemistry of ancient stellar furnaces, gathered by gravity into a world, and sitting there in the dark for billions of years, moving slowly, carrying whatever it carries, being whatever it is. When you think about water that old, something shifts. It stops being a backdrop and becomes a character. The ocean is not the setting of this story. The ocean is the story. Water is the strangest common substance in the universe. It is the only molecule that naturally exists in all 3 phases: solid, liquid, gas, within the ordinary temperature range found on habitable worlds. It expands when it freezes, which means ice floats, which means frozen surfaces insulate the liquid water below rather than sinking and cooling it from the bottom up, which means lakes and oceans do not freeze solid in winter, which means life in those depths survives the cold seasons at the surface. This one quirk of water chemistry, the fact that the solid form is less dense than the liquid, may be one of the reasons life on Earth survived its frozen periods, the Snowball Earth episodes when the entire planet's surface may have been covered in ice. The ocean below kept living because the ice above it floated. On K2-18b, this property of water still holds in the upper ocean. But at the depths where pressure transforms water into high-pressure ice, the physics changes. The exotic ice phases that form under extreme pressure are denser than liquid water. They do sink. They do form the floor, which means K2-18b's ocean has a solid bottom made not of rock, but of a kind of ice that nothing on Earth resembles, cold and hard and crystalline in ways that our familiar ice is not, a floor of pressurized water in a state that requires the weight of an entire world, ocean to create and maintain. And above that floor, rising through hundreds of kilometers of dark, cold liquid, the hydrothermal vents push their mineral plumes upward and the chemistry begins. Picture one of those vents. Not the dramatic black smokers of Earth's deep ocean, though the principle is similar. Imagine something quieter, more diffuse, a field of low structures on a floor of strange ice, warm water seeping upward rather than jetting, carrying dissolved minerals and sulfur compounds and hydrogen in concentrations that are, to the right kind of chemistry, a feast. The water around the vent is warm, not hot enough to be hostile, warm in the way a heated room is warm after coming in from the cold, and in that warmth, in the mineral-rich water rising from the vent field, something has been happening for longer than the continents of Earth have existed in their current form. Membranes. That is where it begins, if it has begun. The simplest possible biological structure, a layer of molecules that separates an inside from an outside, that concentrates chemistry on one side of a barrier and lets the outside remain different. On Earth, the first membranes were likely lipid bilayers, fatty acid molecules that self-assemble in water into hollow spheres because of the way their hydrophilic and hydrophobic ends interact with water molecules. They do this spontaneously, without instruction, without a blueprint, just chemistry, doing what chemistry does when the conditions are right. Those first hollow spheres, billions of years ago in Earth's warm coastal pools or hydrothermal vent systems, became the first cells, not because anything guided them, because the physics of the molecules made it inevitable under the right conditions. Those conditions, warm water, mineral gradients, chemical energy, time, exist in K2-18b's vent fields. They have existed there for longer, perhaps, than they existed on early Earth before life began. And the question the universe is slowly, silently answering is whether the chemistry that self-assembles into membranes on Earth does so because of something specific to Earth, or because of something specific to chemistry. If it is the latter, then somewhere in the warm upwelling water above those vents, in the long, quiet dark of a world ocean, hollow spheres have formed. Hollow spheres containing slightly different chemistry than the world outside them. Hollow spheres that persist longer than the random chemicals around them because the membrane protects what is inside. And in the protection, in the difference, in the maintenance of that difference across time, the first whisper of life. This is the part of the story that moves slowly because it has to. Because what happened in those early oceans, here on Earth or anywhere, did not happen quickly. It happened across timescales that make the whole of human history look like an afternoon. The first living molecules, wherever they arose, spent hundreds of millions of years as almost nothing. Single cells, replicating, making copies of themselves with occasional errors that were sometimes fatal and occasionally useful. The errors that were useful propagated, the errors that were fatal did not. Over time, very slowly, the errors accumulated into something we would recognize as adaptation, as evolution, as the grinding forward motion of life refining itself against the pressures of its environment. On Earth, the first 2 billion years of life were entirely microbial. Bacteria and their relatives, invisible, forming thin mats on the floors of shallow seas, building stromatolites, layered mineral structures that are among the oldest fossils we have, and doing nothing from the outside that looked like the extraordinary thing it was, just chemistry, just cells dividing in the dark, and yet it was everything. It was the foundation of every living thing that followed. Every fish and fern and dinosaur and human being is the downstream consequence of those first 2 billion years of invisible microbial work. K2-18b, if it is alive, may be at exactly that stage. 2 billion years of microbial ocean. Nothing that swims in the way a fish swims. Nothing that sees or feels or navigates. Just chemistry organized into cells, organized into simple communities, releasing their metabolic byproducts into the water and the air above, including dimethyl sulfide, including methane, including the fingerprint that a telescope 124 light-years away, built by the microbial descendants of Earth's own ancient ocean floors, has just barely begun to read. There is a completeness to that image that the mind wants to sit with. 2 biospheres, one ancient and complex and conscious, one ancient and simple and invisible, separated by 124 light-years, connected by a molecule and a mirror. Both of them the result of the same universal chemistry, the same lipid membranes and carbon chains and energetic gradients, working out the same problem in different oceans under different stars. And one of them, the complex one, has just learned to look far enough to see the other. The molecule dimethyl sulfide has a smell. If you have ever been near the ocean on Earth, a real ocean, not a pool, not a lake, but a living marine ecosystem, you have smelled it. That particular oceanic quality, the deep water smell that is slightly sulfurous and profoundly alive, is largely DMS. It is produced by the phytoplankton being grazed and broken down, released into the air above the sea, contributing to the formation of cloud condensation nuclei, affecting the climate by seeding clouds. The smell of the ocean is, in part, the smell of life, the smell of photosynthetic organisms being eaten, the smell of biology cycling through its processes in the surface waters of a living sea. That smell, that specific, recognizable, living ocean smell, is what the James Webb Space Telescope detected at a distance of 124 light-years not the smell itself, obviously, but the molecule that makes it, the chemical compound that carries it. And the knowledge of what that compound means here on Earth is what makes its presence in another world's sky feel like more than data. It feels like a recognition, like something familiar arriving from somewhere impossibly far away, like walking into a room and smelling your grandmother's kitchen and being transported instantly back to a specific afternoon, except the room is an alien sky and the smell is a molecule, and the afternoon is billions of years of ocean chemistry on a world you will never visit. The poets always knew the ocean was alive. Long before science had the instruments to confirm what they felt, people who stood at the edge of the sea understood that it was not just water, that it had a presence, that it moved in ways that suggested something deeper than simple physics. They were not wrong. The ocean is alive. It is alive because billions of organisms are living in it and through it, shaping its chemistry and its clouds and its climate, breathing into it and out of it, building the smell of the sea one DMS molecule at a time. The poets felt what the science has now confirmed, and the science has now extended that confirmation to another ocean, on another world, under another sky. Let yourself feel, just for a moment, what that means. Not think it, feel it. Because the thinking has been done, carefully and rigorously, by the researchers who built the telescope and analysed the data and wrote the papers. The feeling is what remains for the rest of us. The feeling that the universe is not empty, that the darkness between the stars is not purely absence, that somewhere, in the warm upwelling water above a vent field on a floor of exotic ice, something is alive in the oldest and most fundamental way, turning chemistry into persistence, turning energy into existence, and releasing, as the quiet evidence of its being, a molecule that smells like the sea. There is a researcher who described the moment of seeing the DMS signal in the Webb data as the closest thing to a religious experience she had had in science. She was careful to qualify it. She said the signal might not be confirmed. She said the biological interpretation was not certain. But she said that when she first saw the absorption feature in the spectrum, when she recognized what molecule it corresponded to, she had to put down her coffee and sit very still for a while. The data did not change. The uncertainty did not change. But something in the quality of the question changed. It stopped being theoretical and became actual. Not answered, just actual. Real. The thing they had been asking might have an answer, and the answer might be yes. Sitting very still, that is the appropriate response to this kind of data. The universe has been sitting very still with its answer for billions of years, not in any hurry to share it, waiting for someone to build the right question and aim it in the right direction. And now the question has been aimed, and the answer is stirring, moving toward the surface the way DMS moves through an ocean, slowly, diffusely, following the gradient of pressure and chemistry upward through layers and layers of everything that separates the deep from the light. The atmosphere of K2-18b deserves a moment of attention on its own terms. Most of what we know about planets comes from the light that reflects off them or passes through their edges. The atmosphere is the part of a planet that is most accessible to our instruments, the thinnest layer, the outermost edge, the place where the planet meets space. And yet the atmosphere is also, in many ways, the most diagnostic layer. It contains the record of everything the planet does. Volcanism releases certain gases, impacts leave chemical signatures. Biology, where it exists, fills the atmosphere with the chemicals it produces and the chemicals it needs. The atmosphere is the planet's breath, and like breath, it tells you something true about the body it comes from. K2-18b's atmosphere breathes hydrogen and methane and carbon dioxide, and if the signal holds, dimethyl sulfide. It is a thick atmosphere, much thicker than Earth's, held in place by the planet's stronger gravity, and fed by whatever processes are occurring on and in the planet below. It would not be breathable by any human standard. Hydrogen is not toxic, but it is not what our lungs are built to extract oxygen from, and the methane and sulfur compounds would be overwhelming. But breathability is a human concern, and K2-18b is not a human world. Its atmosphere is breathable by whatever lives beneath it, if anything does, in exactly the way Earth's nitrogen-oxygen mix is breathable, only because life here evolved to use it. The atmosphere and the life that produces it are not separate things. They co-evolve. They shape each other. The atmosphere of K2-18b, if it is biological, is both the product of life and the evidence of it. the world breathing out what the life within it has breathed in and transformed. Above the atmosphere, the star K2-18 sends down its light, infrared and near-infrared mostly. The light filters through layers of hydrogen, scattered and absorbed and partially transmitted, arriving at the ocean surface in a quality unlike any light on Earth. Dim, redshifted into wavelengths that feel more like warmth than brightness. If you were somehow suspended at the ocean surface of K2-18b, looking up through the hydrogen sky at the star, it would not dazzle you the way the sun dazzles here. It would glow, deep orange, close, large, steady. A permanent ember in a sky that is never truly blue, never truly black, always that transitional amber red that has no name in our vocabulary of colour because we have never needed a name for it. And looking down from that surface into the water, you would see nothing. The ocean below would be dark immediately, not the gradual deepening of light through Earth's clear tropical waters, not the slow fading from turquoise to deep blue, but an immediate comprehensive darkness, because K2-18b's ocean is not like Earth's tropical shallows. It is deep from the very surface, cold and dark and immense. Whatever lives in it lives below the surface light almost entirely, in the perpetual night of deep water, guided by chemical gradients and thermal currents rather than by sight. Sight, in fact, may be unnecessary in K2-18b's ocean. On Earth, vision evolved because light was available and useful. In the sunlit zones of Earth's oceans, the ability to detect light confers enormous advantages, finding food, avoiding predators, navigating. But in the deep ocean, in the eternal dark below the photic zone, eyes are less useful. The creatures that live there navigate by other means, by pressure gradients, by chemical trails, by the lateral lines that detect water movement, by bioluminescence used not for navigation, but for communication or luring prey. In K2-18b's ocean, where darkness is the dominant condition through most of the water column, life, if complex enough to have sense organs at all, which is far from certain, would likely be oriented toward chemistry. Toward the chemical signatures of warm vent water rising from below, of organic molecules drifting on currents, of the metabolic byproducts of other organisms nearby. Life there might be, in a strange way, more chemical than visual, more about smell than sight, if those categories mean anything at the scale of the organisms we're imagining. Single-celled organisms, of course, do not smell or see. They respond to chemistry directly, through the chemistry of their own membranes, through receptor molecules that bind to specific compounds and trigger responses. This is chemotaxis, the ability of a cell to move toward or away from a chemical gradient. Bacteria on Earth do it constantly. They swim toward nutrients. They swim away from toxins. They navigate their world entirely through the chemistry of it, without any sensory organ we would recognize. If K2-18b's ocean holds microbial life, that life would be doing this in the dark water above the vent fields, following gradients of hydrogen sulfide and mineral compounds and organic molecules, living its small chemical life in the warm, upwelling water of a world that does not know it is being watched. It is being watched. From 124 light-years away, by a mirror in space and the minds of researchers who have spent their careers preparing for exactly this possibility, the watching is new. The life, if it is there, is not. There is something in that asymmetry, something old being noticed for the first time by something young, that carries an emotional weight that does not require explanation. You feel it, or you do not. A parent finding a child's drawing made decades ago, a geologist cracking open a rock and finding a perfect ammonite, coiled and intact, from 200 million years before. The thing was there all along. It was just waiting for the looking, and now the looking has begun, and the thing, the ocean, the molecule, the possible life in the dark water of another world, is yielding its secret one careful observation at a time. The cold of the deep ocean on K2-18b is a particular kind of cold, not the dry bite of space, not the burning cold of liquid nitrogen. Cold like the inside of the Earth at a great depth, pervasive, stable, neither increasing nor decreasing, held in equilibrium by the mass of water above and the warmth seeping from below. The water temperature in the middle layers of the ocean, far from the vents and far from the surface, would be something close to just above freezing, a few degrees above 0 Celsius, the kind of temperature that slows everything down. Chemical reactions proceed more slowly in cold water. Metabolisms are slower. The pace of life, if there is life, would be slower than anything on the surface of Earth. Generations that take years rather than hours. Evolutionary change measured in geological time. A biosphere with a heartbeat so slow that an entire human lifetime would pass between one beat and the next. And yet it would be alive. Slow and cold and dark and vast, but alive in the same fundamental way that a sleeping body is alive, maintaining its chemistry, preserving its difference from the environment, waiting in its own way for the conditions that let it move and grow and divide. The universe does not require speed. It does not require warmth. It requires only the right chemistry and enough time, and it has provided both, in this ocean, in quantities that make even the imagination run quiet. The quietness is right now. Let it be right. The vent fields below and the amber sky above and the dark kilometers between them, all of it turning slowly in the gravity of a smaller star, all of it older than the mountains of this world, all of it carrying in its chemistry the possibility of an answer to the oldest question. The water moves, the molecules rise, the star glows its patient ember above a hydrogen sky. And somewhere in the middle of all that depth and dark and ancient chemistry, in the place where the conditions have been right for long enough, something small and persistent and alive is going about the business of existing, without urgency, without awareness, without any sense that it has been found. But it has been found, or something very like it has, and the finding is not over. The instruments are still running, the data is still accumulating, the researchers are still working through the numbers, and the next generation of telescopes is still being designed, and the question is still open. In the most alive and urgent way, a question can be open, not unanswered because it is unanswerable, but unanswered because the answer is almost within reach, because the instruments are almost good enough, because the signal is almost strong enough, because we are, in this particular moment in the history of a species that learned to look up, almost there. The ocean waits. The molecule rises, the light travels. The journey is slowing now, not ending. Just slowing, the way deep water slows everything that moves through it. The way distance softens sound until it becomes something you feel rather than hear. We have been in this ocean for a long time tonight. Long enough that the darkness of it has become familiar. Long enough that the amber sky above and the exotic ice floor below feel less like descriptions and more like places. The vent fields are somewhere beneath us, their warm plumes rising in the cold dark, and the hydrogen sky is somewhere above, and between them the water holds its chemistry and its currents, and whatever it holds that we have not yet named. The story is turning now toward rest, but it is still moving, it is still going somewhere. The ocean does not stop because the hour is late. There is a question that was placed quietly in the middle of this story and left there, waiting. It was the question of whether life on K2-18b, if it exists, is alone in its ocean the way life on early Earth was alone in ours. The only thing, the only chemistry that had crossed the threshold, surrounded by a vast and indifferent sea. Or whether the ocean, of K2-18b being so much larger and older, might have crossed that threshold many times, in many places, independently, producing not one lineage of life but several, each arising from its own vent field, or its own warm pocket of chemistry, each developing in isolation from the others in an ocean so enormous that two lineages could exist for millions of years without ever meeting. On Earth, all life shares a common ancestor. Every organism that has ever lived on this planet descends from a single original lineage, a single crossing of the threshold from chemistry to biology. We know this because the genetic code is universal, the same codons, the same 20 amino acids, the same basic molecular machinery, in bacteria and oak trees and deep-sea fish and human beings. One origin, one family. The entire tree of life on Earth is a single tree, not a forest, but that may be an accident of Earth's size. Earth's oceans are small enough and interconnected enough that a single successful lineage could spread everywhere before another independent origin had the chance to establish itself. If a second origin occurred, it may have been outcompeted and absorbed before it had the chance to diverge. We would never know. The winner, as always, wrote the only history that survived. K2-18b's ocean is 6 times larger than Earth's total surface, divided by depth into layers of different chemistry and temperature and pressure, divided by the enormous distances between vent fields. An organism arising near one vent system in the southern hemisphere of a world ocean would have no mechanism for reaching a vent field on the other side of the planet, not in any reasonable time frame, not at microbial speeds, not across hundreds of millions of kilometers of cold open water. The vent fields are islands in a sea of sea, and on islands things evolve independently, separately, into forms that share a principle but not a history. If K2-18b's ocean has been alive long enough and is large enough, it may harbour not one kind of life but many. Not many species in the way Earth has many species, all related, all sharing the same genetic machinery, but many independent origins. Many separate experiments in the chemistry of persistence. Each one a different answer to the same question, each one arising from the same universal principles of chemistry and energy, and membrane and replication, but arriving at those principles from a different starting point, a different local chemistry, a different set of available molecules, a forest of life, not a single tree. That idea, multiple independent origins of life in a single ocean, is one of the most quietly radical concepts in astrobiology. It would mean that life is not just possible in the universe, it would mean that life is easy, that given the right conditions, it does not arise once and spread, but arises again and again independently, like fire arising in different parts of a dry forest from different lightning strikes, each fire finding its own fuel, burning in its own way, filling its own niche. A universe not of rare exceptions, but of ordinary occurrences. Life as common as water. Life as inevitable as chemistry. We do not know if this is true. We cannot know yet. But K2-18b, with its world ocean and its ancient vent fields, and its dimethyl, sulfide and its methane, is the place where we are most likely to find out. The water is quieter now in this part of the story. The current that has been carrying us through the science and the wonder and the emotional weight of all that wondering is still moving, but gently, the way a river moves near its mouth, where it widens and slows before it meets the sea. The James Webb Space Telescope has a finite lifespan. It was launched in December 2021 with enough fuel to last approximately 20 years at its operating position at L2. By the time it exhausts its fuel, it will have changed astronomy irreversibly. It will have looked at the first galaxies. It will have mapped the atmospheres of dozens of exoplanets. It will have found, in the spectrum of a world called K2-18b, a molecule that made the people who found it go quiet. And then, when its fuel is gone and it can no longer maintain its precise orientation in space, it will drift. It will not fall. It will simply drift, slowly in its orbit around the sun, the mirror still cold, the instruments still intact, the data long since transmitted and stored and analysed and published and argued, over and built upon. It will drift for a very long time, a monument of sorts, a place where the question was first asked seriously enough to receive an answer. The next generation of telescopes will be different, larger, more capable. The Habitable Worlds Observatory, currently in planning stages, is being designed with exactly this purpose in mind. The direct detection of light from Earth-like planets orbiting Sun-like stars, the imaging of worlds, the spectroscopy of their atmospheres at resolutions that Webb cannot achieve. It will not be ready for many years. Science at this scale moves slowly, funded in pieces, designed over decades, built by teams of hundreds who will retire before it launches, but it is being built. The question is serious enough now that the answer is being resourced. When that telescope looks at K2-18b, and it will, K2-18b will be among the first targets of every next generation instrument. It will see what Webb could only hint at. It will resolve the DMS signal definitively. It will find or rule out the suite of other biosignatures. It will either confirm that the ocean of K2-18b is alive, in which case everything changes, or it will find that the signals had geological explanations, in which case science adjusts and looks elsewhere, undiscouraged because the universe is large and the number of ocean worlds it contains is vast, and the question remains open and the looking continues. The looking always continues. That is the thing about curiosity. It is not satisfied by a single answer. Each answer opens a new question. Even a confirmed detection of life on K2-18b would immediately generate 1,000 new questions. What kind of life? How complex? How old? How distributed? Are there multiple independent origins? Is there any analogue to multicellularity? To the extraordinary step that life on Earth took about 600 million years ago when single cells began cooperating, sharing functions, becoming something larger than any one of them could be alone. Is there anything in K2-18b's ocean that is not a microorganism? Is there anything that moves with purpose, that responds to light or chemistry in ways that suggest even the simplest form of organised behaviour? These questions are premature. We have not yet confirmed the first step. But the mind moves ahead of the instruments, as it always has, preparing the questions before the answers arrive. That is not impatience. It is readiness. It is the mind doing its work. The currents of K2-18b's ocean would be, in a very old ocean with no continents to disrupt them, extraordinarily stable. The great gyres we imagined earlier, the slow circling patterns of water driven by the planet's rotation, and the temperature differences between the equatorial surface and the deeper cold, would have been running for so long that they have become geological features in their own right. Predictable, consistent. The chemistry that drifts in those currents has been drifting along the same paths for billions of years, the same molecules following the same routes, depositing minerals in the same patterns on the exotic ice floor, concentrating nutrients in the same upwelling zones where cold deep water meets the warmer middle layers. Life, if it is there, would know those currents. Not know in any conscious sense, but be shaped by them, adapted to them, distributed by them. The organisms that produce dimethyl sulfide would be concentrated in the upwelling zones, where nutrients are richest, where the chemistry is most active, where the metabolic resources are highest. And from those zones, the DMS would rise, following the gradient of concentration from the high DMS water into the lower DMS atmosphere, diffusing upward through the hydrogen sky, spreading across the entire planet's atmospheric circulation until it was distributed at low concentrations throughout the whole atmospheric column. When the telescope reads it, it is reading the integrated signal of an entire planetary biosphere. Every DMS-producing organism on K2-18b, in every upwelling zone, in every vent field, over the entire surface of a world ocean, has contributed to the signal. It is the collective exhalation of a biosphere, if it is that. Not one creature, not one place. An entire world breathing together, with no knowledge that it is a choir. The word choir is too human. But the concept behind it, many small things producing together something audible at a great distance, holds. Each individual organism contributing its molecule. Each molecule joining the atmospheric pool. The pool reaching detectable concentration. The concentration being read from 124 light-years away. Many becoming one signal becoming a question. The question becoming a story told at night, carried on words, arriving at the ears of someone lying in the dark and wondering. The connections in this story run in all directions, backward through time to the Big Bang that made the hydrogen in that ocean, forward through time to the telescopes not yet built that will answer the question more completely, outward through space to the 124 light-years of vacuum between here and there, and inward to this moment, this room, this quiet, the particular quality of attention that the late hour and the long journey have produced. Something settles in a long story well told, not resolution. The question is still open, the answer is still forming. But a kind of rest within the openness, the way a ship does not need to arrive to feel the harbour approaching. The motion of the water changes, the wind is different, the quality of the dark shifts. You know, without being told that something is near. K2-18b is still there. It was there before you started listening and it will be there long after. The ocean turns. The vents breathe their mineral plumes into the cold dark water. The molecule rises. The star burns its patient ember above the hydrogen sky. None of it hurries. None of it waits for confirmation or consensus or the completion of another observing cycle. It simply is, in the way that old things simply are. Present, continuous, indifferent to the watching, and yet somehow changed by it, the way any observed thing carries the mark of being seen. The researchers who made this discovery went home that night, after the data review, after the careful language of the preprint was drafted, after the uncertainty was quantified, and the alternative explanations were listed, and the cautious conclusions were drawn. They went home to ordinary houses in ordinary cities. They ate dinner. They may have looked up at the sky, not at K2-18 specifically. It is not visible to the naked eye, too dim, too distant, just one of the invisible stars in a sky full of invisible stars. but they looked up at the sky knowing what they knew, that in the direction of the constellation Leo, at a distance of 124 light-years, something in an alien atmosphere had been found that should not be there if the universe is empty. That knowledge does not wash off in the shower. It does not settle back into the ordinary texture of daily life. It changes the background of everything. The way the discovery of deep time changed everything for the geologists who first understood it. The way the discovery that Earth orbits the Sun changed everything for the people who first accepted it. Once you know the universe is this large and this old and this various, you cannot unknow it. The scale becomes part of how you see everything else. Small things become smaller and more precious. Large things become larger and more patient. The middle things, the ordinary human days, the meals and the conversations and the small decisions, remain exactly as they are, and that is the strangest comfort of all. The middle things are where life happens, even for the researchers who spend their professional hours thinking about other worlds. Even for the microorganisms in K2-18b's ocean, if they are there, life happens in the middle. Not at the crushing floor and not at the violent atmospheric boundary, but in the middle layers where the conditions are moderate, and the chemistry is active, and the pressure is survivable, and the temperature is cold enough to slow things down but not cold enough to stop them. The middle is where persistence lives, and persistence, the maintenance of difference, the holding of inside against outside, the slow accumulation of generations, is what life is at its most fundamental. Not intelligence, not beauty, not consciousness, just persistence, the stubborn chemical fact of continuing. K2-18b has been persisting for billions of years. Whatever is in its ocean has been persisting for nearly as long, and the universe, which has been persisting since the beginning of everything, is patient enough to let the answer arrive in its own time, through its own instruments, at whatever pace the chemistry of understanding requires. The pace, tonight, has slowed to something almost restful. The great distances are still there, but they feel less daunting now. The questions are still open, but they feel less urgent. The ocean is still vast and dark and cold, but it is a familiar darkness by now, the kind you have been sitting with long enough that it no longer requires adjustment. The star K2-18 is somewhere above the horizon of its planet right now, on the side of the world that faces it in its 33-day orbit, casting its amber light onto the surface of the ocean, warming the upper layers slightly, driving whatever photochemistry or photosynthesis occurs there. On the night side of the planet, the side currently turned away from the star, the ocean surface is in true darkness. No moon is confirmed for K2-18b, so there is no reflected light, no tidal influence of a satellite, just the planet and its star and the dark between them when the planet's rotation carries any given point away from the light. In that darkness on the night side of K2-18b, the ocean surface is quieter. The convection driven by solar heating is absent. The upper water is cooling slightly, becoming denser, beginning its slow descent toward the middle layers in the thermohaline circulation of a world without continents. The atmosphere above the night side is darker still, but not empty. The molecules are there, the DMS among them, present on both sides of the planet, distributed globally by the atmospheric circulation that moves constantly from day side to night side and back again, driven by the temperature differential between the illuminated and the dark hemispheres. The signal that Webb detected is the signal of the whole planet, day side and night side together, the entire atmosphere integrated into a single spectrum, which means the life that produced it, if life produced it, is not confined to the sun-facing hemisphere. It is distributed across the whole world. It lives in the dark as well as the light. It has no preference for day or night because it does not, at the level of its simple chemistry, distinguish between them. There is something right about that, for this hour. Life that does not distinguish between day and night. Life that persists in the dark with the same quiet chemistry it uses in the light. Producing its molecules in the deep cold, sending them upward through the water and the air, regardless of whether the star is visible or hidden, regardless of whether anything is watching. The ocean of K2-18b does not know it is being watched. The molecule does not know it has been found. The story does not know it is almost over. But you know. And the knowing is its own kind of arrival. The ocean's very quiet now, not silent. The deep water is never silent. There is always the slow movement of current, the pressure of depth, the faint thermal noise of molecules in motion. but quiet in the way that old things are quiet, the way a library is quiet, the way stone is quiet, a quietness that has been accumulating for so long it has become structural, load-bearing, part of what holds the world together. We're in the deep part of the night now. The story has come a long way. K2-18b turns in its orbit, 33 days to circle its star, and right now, in this moment, it is somewhere in that circuit. The ocean moving beneath its hydrogen sky, the vent fields breathing upward in the dark. Nothing has changed since we first arrived here. The ocean was turning when we came, and it is turning still. It will be turning long after this night is over. The molecule dimethyl sulfide is in the atmosphere above the ocean. It has been there, if the signal is real, for longer than human civilization. It will be there tomorrow night and the night after. The telescope at L2 will look again. The data will accumulate. The picture will clarify slowly, the way all true things clarify, not all at once but by degrees, each observation adding its small weight to one side of the question until the balance tips and the answer becomes clear. But that is for another time, not tonight. Tonight the water is dark and the currents are slow, and the cold of the middle ocean is the kind of cold that does not demand anything. It simply is. It holds the chemistry of the water in its steady hands, neither helping nor hindering, just present, just the temperature that the depth and the distance from the star have made it. Somewhere in that cold, a membrane holds, inside it, slightly different from outside. The difference maintained by chemistry too small and too patient to be called effort. Just persistence, just the quiet fact of continuing. The star above the ocean does not know the ocean is there. Stars do not know things. They burn. They give off light. The light falls on the hydrogen sky and filters down in red and amber wavelengths to the surface of the water, and the surface of the water receives it without acknowledgement. The receiving is just physics, just photons striking molecules and transferring energy. But in the right chemistry and the right conditions, that transfer becomes something else, becomes the first step of metabolism, becomes the first link in a chain that ends in a molecule rising through kilometers of water and air and space to a mirror. The chain is very long, each link is very small, together they cross the universe. That is enough for tonight. The chain exists or may exist, and the possibility of it is one of the most extraordinary things the human mind has ever been asked to hold. You have held it. You have carried it through the vent fields and the pressure zones and the amber sky and the absorption lines of a spectrum red in cold space. You have followed it all the way here to the quiet end. The deep ocean of K2-18b is very still in its lowest layers. Above the exotic ice floor, above the vent fields, in the column of cold water that rises through hundreds of kilometers toward the surface, the water barely moves. It drifts. It carries what it carries. It goes where the slow gradients of temperature and chemistry take it, without urgency, without direction that could be called intentional. Just drift. The atmosphere above the ocean drifts too. The demess in it moves on the planetary winds, spreading from the upwelling zones where it is produced, thinning as it spreads, becoming part of the background chemistry of a world's air. From space it is detectable only as an integrated signal, faint, requiring a very cold mirror and a very long exposure to read. It does not announce itself, it simply is. Simple things, persisting. The telescope floats at L2, cold, precise, still. The light travels. You're very far from where this story began and very close to where it ends. The two places feel, at this hour, like the same place. The distance has collapsed into the particular closeness of a long night well spent, the way the end of a journey makes the beginning feel near. K2-18b will be there tomorrow. The ocean will still be turning. The question will still be open, still alive, still the best question anyone has thought to ask. And the instruments will still be looking, patient as the universe itself, building their answer one photon at a time. The vent field is warm below and the water above it rises in a slow plume, and the molecules in the plume drift upward through the cold and the dark, following nothing but the gradient, going nowhere but up, carrying their small chemical signature through the layers and the pressure and the dark toward the surface of a world entirely covered in sea. The surface is quiet tonight on the side turned away from the star. No light, just the ocean and the hydrogen sky and the dark between them. The atmosphere breathes its slow planetary breath. The gases moving in their global circulation, the DMS distributed in its thin whisper across the whole sky of a world that does not know it is being listened to. It is being listened to, and the listening tonight has been enough. The question remains open. The ocean remains vast. The cold remains steady, and the vents remain warm, and the molecule remains in the air of a world 124 light-years away, patient as everything that has existed for billions of years without needing to be found. You found it anyway, in the only way it can be found from here, with attention, with wonder, with the willingness to follow a question all the way to its edge and sit there in the dark and look out over the water. The water is very still now. Let it be still. There is more ocean on K2-18b than one night can hold, and tomorrow, when the dark comes again and the day is set down and the journey resumes, there will be more to find waiting in the deep. The water is very still now. The current that has moved through this entire story, through the telescope and the data and the amber sky and the vent fields and the rising molecule and the open question, has slowed to something barely perceptible. A drift. The kind of movement that is almost indistinguishable from stillness, but is not quite stillness, because nothing in the universe is ever truly still. Everything moves. Everything carries its small momentum forward, even at rest, even in the deepest cold, even in the quietest hour of the longest night. K2-18b moves through its orbit. 33 days to circle its star, and the circuit never stops, and the ocean never stops, and the chemistry never stops, and the molecule never stops rising through the water toward the air, and through the air toward the dark, and through the dark toward whatever instrument is patient enough to find it. The James Webb Space Telescope floats at L2 in its cold and its precision and its silence. It has no sense of the importance of what it does. It simply collects light. It has been collecting light since December 2021, and it will collect light until its fuel runs low and it drifts, and even then the light will still be travelling, still crossing the distance, still arriving at the place where the mirror was, carrying its information through empty space with the patience of something that has been moving for a very long time and does not know how to stop. The ocean of K2-18b does not know it has been found. The microorganism, if it exists in the warm water above the vent field, does not know it has contributed to the most important question a species has ever asked. It simply exists, divides, metabolizes, releases its molecule into the water. The water carries it up, the air carries it further, the light carries it the rest of the way, 124 years at the speed of light, arriving as a whisper in a dataset, becoming a question, becoming a story, becoming this. The deep ocean is cold, and the star is patient, and the night is very quiet now, and the distance between here and there has become, over the course of this long journey, something almost comfortable, a known thing, a place you have been, an ocean you have sat beside long enough that its darkness feels familiar, and its cold feels like rest, and its vast and ancient chemistry feels like the background of something important, something ongoing, something that will still be happening tomorrow and the day after and for billions of years after every instrument we have ever built has gone silent. The ocean persists, the question persists, and you, having travelled this far tonight, having carried the weight of the wondering all the way to the edge of sleep, can set it down now, not because it is answered, but because it is safe. The ocean is there, the molecule is in the air, the telescope is looking. The answer is forming slowly in the way that all true answers form, not all at once, but quietly, by accumulation, in the dark, while everything rests. The water is very still, the star is very far, the night is deep enough now to sleep in, and there is nothing left to do but drift. The way the molecule drifts, the way the current drifts, the way everything drifts in the end toward the quiet place where motion becomes rest, and the journey becomes a dream, and the dream becomes the dark, and the dark becomes the deepest, softest, most patient thing there is. The ocean of K2-18b will be there tomorrow night, and it will have kept its secrets carefully, and there will be more of them waiting in the deep than one night could ever hold.